smart of it. We want to wait just a minute to give people a little bit more time to get logged in.
We have about 96 attendees. Did we check? We have someone was saying they were having trouble with the conference code. Hopefully that's resolved.
Yeah, I saw.
The code is not. Maybe they're missing the pound at the end. It's a possibility.
So maybe we can go ahead and start.
Yeah. All right. I think we could go.
Yeah.
Go ahead. Okay. Well, thanks to everyone for joining us today. This is the second session of the USGS Hydrography Webinar Series. I'm Al Ray, and I work with Jeff Simley, who's co-manager. Together, we're co-managers of the NHD. I'd also like to acknowledge Steve Achel, who will be helping with questions and answers later on, and Allison Jason, who's helped us with WebEx Training Center technology and a lot of other things. There are also many other people who've been helping make this webinar series possible, but there are too many to name here. So we'll move on. Looks like we've got a little bit over 100 people online now. I'll go over here. This is the agenda for today's seminar. I'll have some brief introductory comments about the Hydrography Webinar Series, and then I'll give a short overview of how the flows are computed using NHD+. Then Ed Clark will give us the feature presentation for today about the National Flood Interoperability Experiment. We'll have some time for questions and discussion after Ed's presentation. Let's see, I got to advance the slides.
Al, just one moment. We have a question on the line about muting, and I want people to know we've muted everyone's line except for the people that are speaking. So, you know, you won't be able to be heard on the line to share that, because there was a chat question about it.
All right, thanks, Allison. So I want to give a little bit of introduction to the webinar series. This is our second in the series, and we had three basic purposes for the webinar series that we're showing here. First, we'd like to share success stories from users who solved real-world problems using hydrography data. We're also going to provide some information on the NHD and the WBD and other related products. And finally, we want to provide a forum to our user community similar to a conference setting. In these days of shrinking budgets and travel restrictions, we felt there's a place for a virtual conference of this sort. So these are some of the topics we hope to cover during the seminar series. The list isn't intended to be exclusive, though, so please let us know if there are other topics that you'd like to see covered. We plan to use the webinars, we plan the webinars to be a mix of presentation types. We'll have users describing how they've used hydrography data to solve a particular problem. We'll have presentations on the underlying technology and the data. We also plan to have some rapid-fire sessions in which several presenters will give very short 5-minute presentations just to give us a quick overview of what they're doing. And we'll also try to collect your feedback on what you want to see in future seminars. These are some of the ways that you can get more information about the webinar series. The main resource is the webpage shown on the top here. Note that the URL is case sensitive. We also have a newsletter that Jeff Simley sends out each month. If you'd like to be on the mailing list for the newsletter, send us an email. We will send out announcements for future webinars through the AWRA and some of the other organizations. So also when you sign up for one of the webinars, we'll put you on a list for future webinar announcements. We promise not to spam you with other stuff from this list. We plan to have webinars every 6 to 8 weeks. So we've placed all the phones except for the presenters on mute to minimize background noise during the webinar. If you have a question, please find the Q&A tab, which is has a question mark icon in the upper right of the WebEx window, and you can type in your questions there. If you've made your screen full screen, the presentation full screen, then the Q&A options are on a pull-down menu that appears when you put your cursor near the top of the screen. We'll monitor the Q&A list for questions from participants, and we'll ask the presenter to answer some of them during the discussion session. We'll post written answers to all the questions later on the seminar series website. So we'd appreciate it also at the end if you'd take some time to answer a few very short questions at the end of the seminar to help us improve future webinars. So now I'll start with a very short presentation on the NHD Plus, because both last month's presentation by Bill Samuels on river spill and icy water and today's presentation on flooding by Ed Clark, both those use the NHD Plus for flow computations. So I want to give you some background on how the flows can be computed using NHD Plus, and specifically how the mean annual and the mean monthly flows that are included in NHD Plus were computed. I'm going to cover this pretty quickly and at a very high level. There's a lot more information about this in the NHD Plus user guide if you'd like to know more information. Oops, I got lost here. Sorry, I lost my place. Okay, I'd like to take a moment here to acknowledge the really very small team that's been working on the NHD Plus for the last decade or so. The team you see here, led by Tommy Dewald at the EPA, conceived and developed the NHD Plus. An interesting thing about this team is that they've only met all together in person just a few times over all these years, but they've spent probably close to 1,000 hours on the phone discussing every aspect of NHD Plus. And I'm not kidding, 1,000 hours is actually a pretty good estimate of the time. And version 2 of NHD Plus was actually produced entirely virtually. The team didn't meet at all in person during the production of NHD Plus version 2. So I think it's a testament to how much a small team can accomplish given the right technology. And personally, I'm very proud to have been a part of all of this. So here's an overview of what I'll cover in this presentation. First, I'll talk about the major components of the NHD Plus that are used in flow computations. These include the surface water network, the NHD Plus network attributes, catchments and catchment and watershed attributes, and points of interest that are linked to the network, such as gauges, model forecast points, and dams. Then I'll talk about the specific example of the flow analysis that's included in the NHD Plus, which is called the EROM, or the Enhanced Runoff Method, for computing flows and velocities. These are the major components of the NHD Plus, with the vector data on the left and the raster data on the right. The NHD Plus includes a snapshot version of each of the 3 major data sets that were integrated to create NHD Plus. And this includes the complete 1 to 100,000 scale NHD, the watershed boundaries data set, and the National Elevation Dataset on the raster side. NHD Plus also includes the actual features that were used to do hydro enforcement of the elevation data and the catchment polygons that are one of the major products. We also include the hydro enforced DEM, the flow direction and flow accumulation grids, a raster version of the catchments, and lots of attributes. So the NHD Plus has a set of attributes that are known as the value-added attributes, or VAAs. The VAAs encode lots of information about the stream network, and they enable many different kinds of analyses. Shown here are a few of the attributes that are used for analysis and navigation. There are several other attributes as well. Today, we're going to focus on the second and third navigation attributes, the from and to nodes, and the hydrologic sequence number. So the NHD Plus has a nationally unique set of node IDs. These can be used for node-to-node network walking models, and lots of the traditional flow models fit into this category. So an interesting thing about these node numbers is that they're entirely conceptual. They exist in a flow table that identifies the stream flow lines that flow to each node, but there is no actual feature class of nodes in the data set. And probably the most important of the value-added attributes is the hydrologic sequence number. The hydro sequence number is designed so that from any flow line in the network, all the flow lines that are upstream have a higher number, and all the flow lines that are downstream have a lower number. This is pretty amazing since the national stream network is a whole lot more complex than the one that's shown here on this slide, and it includes many thousands of divergences. In other words, it's not a simple dendritic network. The one really useful aspect of hydro sequence numbers is that if you sort them in descending order, you can walk through the entire network and do some process like computing drainage area. And wherever you are in the network, you will already have processed everything upstream of you. And all you have to do is add up the upstream areas. So this means you can do processing like this in a single pass through the entire network. And that makes the processing very efficient. So we can use attributes like the hydro sequence number along with several others to do network navigation using database queries. So if the network was simple and dendritic, I could pretty easily explain what the queries are. But because we have divergences in the network, the queries are a bit more complex. They're still queries, though, and databases are really good at doing queries very fast. So the NHD Plus has a tool that can do network navigation using queries, and it can do these 4 types of navigation: upstream main stem, upstream with tributaries, downstream main stem, and downstream with divergences. The tools support a variety of stop conditions too, like stopping the trace after going 50 miles upstream, for example. And finally, because these are all database queries, they're really fast and they can work efficiently on really large navigations. The VAA navigation tool is available as a toolbar in ArcMap, and it's also available as a DLL that you can call from your own custom program, like a Python script. So with this tool, it'd be pretty easy to make a script that can do some very sophisticated network-based analysis. Here's a simple example using the tools showing an upstream main stem and an upstream with tributaries navigation for the Susquehanna River. Both these navigations happen very fast. A Aside from the stream network via A's, probably the next most important feature in the NHD Plus is the catchments. Catchments are the immediate areas that drain to each segment of the stream network. I'll show a picture of some catchments in a moment. On this slide, I have some details about how the catchments are computed, but the most important thing that I want you to know about catchments is the last point. They really are the key to understanding and connecting the landscape with the stream network. That's important because overland flow is quite different than flow in channels. And it's in this process that a lot of things can happen, such as pesticides being washed off a field and into a nearby stream, and so on. So catchments really are the key to understanding how landscape attributes like land cover or geology or soils affect stream flow. So the way that we compute catchments is by combining the NHD streams and water bodies, the watershed boundaries, and elevation data. So exactly how we do that is a topic for another day. But for now, just understand that this process is the key to getting catchments in NHD Plus. So here's a picture of some catchments. You can see there's a catchment for each line segment in the NHD network. There are catchments also for each coastal line segment. The catchments in the NHD Plus cover the entire continental U.S. So if you drop a hypothetical drop of water anywhere in the 48 states, you can know instantly where in the stream network that drop of water would go simply by intersecting the point where it falls with the catchment data set. So the NHD Plus version 2 includes the catchment attributes that you see here. There are mean annual and mean monthly precip and temperature, as well as runoff from a simple water balance model that was developed by Dave Wallach and Greg McCabe. There are also all the categories of the 2011 National Land Cover Dataset. And for all of these, we have both the attributes for each individual catchment, but also the accumulated attribute for each catchment. And that includes all the catchments upstream of it. There's also a mean latitude for each catchment, but this one isn't accumulated for upstream catchments. So all these attributes, except for the NLCD, were used to compute the flow estimates that are included in the NHD Plus. So now that we have a stream network and catchments, we need to tie some observations to the structure. Here's some examples of the kinds of observations and points and lines that we can link to the network. There's really no limit to the kinds of things that we could link to the network. So we do this in GIS using something called linear referencing, which is similar to mile markers along the highway. We don't have time to get into those details right now, though. For the flow analysis, we're going to be looking at the stream gauges are the things that we're most interested in. Now I'm going to give you a really brief overview of a specific example of streamflow modeling, and that's the one that's used in the NHD Plus itself to compute the mean annual and the mean monthly flows. It's called the Enhanced Runoff Model, or Enhanced Runoff Method, or EROM for short. EROM goes through these steps to compute the flows. The flows are computed for each of the 5 steps, the first 5 steps here in NHD Plus. And then each step gives us an improvement of the estimate. And the results of the 5th step are considered to be the best estimate of the flows. I'll walk through each of these steps very, very quickly, but I would just want you to get a feel for what the process is like. This is the first step, which is a water balance runoff model by Dave Wallach and Greg McCabe. It's developed from the PRISM precip and temperature data for the U.S. and from similar grids that were developed by the Canadian Forest Service for Canada and for Mexico. This graph shows the results of the water balance model. The points are gauges, and if the estimates were perfect, they would all fall right along that red line. The second step is an adjustment for what's called excess evapotranspiration from the streams and from water bodies. And it shows, this graph shows how that adjustment worked for the Colorado River Basin. And you can see it improves the estimate a lot in this region. It has less effect in more humid regions. This graph shows how the step 2 adjustment moved the points closer to the red line. This particular graph is for the lower part of Region 10, which is the Missouri River Basin. Step 3 was a regression of basin characteristics against flows for the gauges. The regression improves the fit of the data quite a bit. Then step 4 lets us account for additions and removals from the flow network. There's a table called Plus Flow AR that contains records that tell us where flows are added or removed from the network. And currently this table only includes a few of the largest water transfers, but the structure is there so that we could represent lots more detail if we had the data to support it. This shows here the results of additions and removals for the New England region. And you can see that for most of the gauges it had no effect at all, but it improved the estimate considerably for that one outlier. And step 5 is an adjustment using the flows from the gauges. So basically, for every flow line that has a gauge, we adjust the flow and match it to what the gauge tells us it should be. Then we adjust the flows on upstream flow lines, and then we reaccumulate those flows downstream. And then finally, there's a process that's done that randomly removes 20% of the gauges just to see how that affects the results, and that gives us an idea of how good the results are in step 5. And this is a picture of the final results. There's a flow estimate for each of the 2.7 million flow lines in the NHD Plus, and here you can see we've set the line width to represent the flows there. So I just want to briefly mention that we're developing NHD Plus now for the high resolution NHD using 10-meter elevation data. But we'll have to cover that another time because we need to move on to our main presentation today, which is going to be Ed Clark's presentation on the National Flood Interoperability Experiment. So Allison, if you could switch over to Ed, I'll do a quick introduction. So Ed is the National Flash Flood Service leader in the National Weather Service Headquarters Forecast Service Division. And prior to joining headquarters, he was the senior hydrologist at the Colorado River Forecast Center in Salt Lake City. Since joining the hydrology team at the National Weather Service headquarters, he has led efforts on behalf of the Office of Hydrologic Development to scope and design the integrated water resources, science and services, interoperability, and data synchronization capabilities, as well as planning for the NOAA National Water Center. Ed's also co-chair, along with me, of the Subcommittee on Spatial Water Data. So, Ed, go ahead and take it away.
Okay, thanks, Al. Can you see my screen?
Yes.
All right. Well, thanks, Al. This is a really exciting opportunity to share how we, within the National Weather Service, and actually across a broad consortium of university and academic partners, are using the National Hydrography Dataset to really explore and push the future of flood forecasting. The National Flood Interoperability Experiment is a little bit of a spontaneous and somewhat serendipitous effort. This is really the brainchild of Dr. David Maidment at the University of Texas, Austin, and has been championed by him among other members of the quasi community. The goal is to explore the future of flood forecasting done at very, very high spatial resolutions, the 2.67 million catchments and stream flow lines of the NHD+. Explore real-time flood information services, the web-enabled services that will share information seamlessly, transparently across the operational forecasting and development and then decision management processes. And then most excitingly, this is an opportunity for us to engage the academic community, explore emerging capabilities through the National Water Center. For those of you who don't know, NOAA, through a directed appropriation, was fortunate enough to build a National Water Center on the campus of University of Alabama in Tuscaloosa. It was completed in 2014, and we're actually cutting the ribbon on that building next week in Alabama. We really hope that this is not only a catalyst for emerging water resources capabilities within the National Weather Service and NOAA, but it serves as a center point for engagement with other federal agencies. Case in point, the USGS is a close colleague with us, not only at Subcommittee on Spatial Water Data, but has been a partner throughout the planning and preparation for the National Water Center, and will continue to do so. So why flooding? Why a national experiment dedicated to exploring alternatives and new ways of doing flood forecasting? I don't think I need to tell this audience that flooding is our most severe form of weather, natural disasters. On average, we lose more fatalities to flooding than any other severe weather disaster. The exception, the outlier here is heat, but we don't classify that as severe. In fact, if we look at the last 100 or so years of flood loss data, we see, and extrapolate that forward, we can anticipate that flooding will cost the nation, direct impacts of losses due to flooding will cost the nation a delta of $300 billion, and that we run the risk of losing an additional 2,500 lives. To put that in perspective, $300 billion is greater than the cost of the national highway system throughout its 60-year development, and 2,500 fatalities are more than the men and women, more than fatalities of servicemen and women from since the onset of 9/11. So why is the National Flood Interoperability a use case for the hydrography dataset? Simply put, the hydrography dataset is the language that links together flood forecasting, flood predictions in time and space with the expected impacts. It is the framework that allows us to seamlessly communicate between where a point is modeled and forecasted and where those impacts may be conflated. So it facilitates this next generational hydrologic modeling. I'll describe a little bit about the basis for its use within the modeling components of the National Flood Operability Experiment. As I said, it is the framework for data conflation, and not just between Weather Service data sets, but with other federal data sets, such as the National Flood Hazard Layer from the Federal Emergency Management Agency. It allows us to intersect projections and forecasts with impacts or data sets from Environmental Prediction Agency. The list is really limitless, and I think Al alluded to that in one of his earlier slides. Any type of data can be mapped to the NHD, and in doing so, it really becomes a very powerful tool for describing not only the impacts of flooding, but other water resource-related variables. And finally, the hydrography, using a common hydrography data set or common language, common mapping convention, provides a framework for the research and academic communities to better tie with federal operational forecasting entities. And the NIFI is not just a one-year experiment. In fact, as the National Water Center is developing its capabilities, many of the types of systems that will be demonstrated and glimpsed during the NIFI will have some longevity for operationalization at the National Water Center. This allows us to go from our current forecasting system of approximately 3,600 locations through our Advanced Hydrologic Prediction Service, AHAPS, water.weather.gov, to over 2.6 million locations. That means that when we get to the instantiation of a WRF hydro-driven forecasting system on the NHD+, the humans will be, on average, no more than a mile away from a discretized forecasting location. And most importantly, this new data sets will inform emergency managers on how they can how they can improve their decision, they can improve their processes for the protection of lives and property. And that's NOAA's and the National Weather Service's main organic mission. So we asked 3 specific questions within the National Flood Interoperability Experiment. How can near real-time hydrologic simulations at very high spatial resolutions covering the nation be carried out using the NHD+? How can this lead to improved emergency response and community resiliency? And in order to test this, we are partnering with members of the emergency management community as well as social scientists. And then finally, how can an improved interoperability framework, as I said earlier, web services, support these first 2 goals and lead to success and sustained innovation in the research to operations process, and more importantly, the operations to research process? So there are 5 major components of the National Flood Interoperability Experiment. There's the there's NIFI-GEO, or the National Geospatial Framework for Hydrology. There's the NIFI-Hydro. This is a coupling of high-resolution hydrologic forecasting, numerical weather prediction models, and downstream routing models. There is a research track within the Flood Interoperability Experiment to explore how river channel information and dynamically generated flood inundation mapping could be carried out or coupled to a national hydrologic forecasting system. And as I just said, there's a component of this that will explore how new data sets, emerging data sets, enabled through web services can be more broadly made available to the emergency response community. I will pause here and say that all of this is done within the confines of a true experiment. None of the information, none of the services from the NIFI will be misconstrued or conflated as operational forecasting. We do this because we can't use the public as a guinea pig. And more importantly, we need to characterize the magnitude, the skill, and the uncertainty in these types of emerging technologies. Nevertheless, it's a very exciting time. So what is NIFI-GEO? At its heart, it is built on 9 feature classes from the NHD Plus version 2. These are the sub-watersheds, the HUC-12, the catchments, the 2.67 million catchments that Al spoke to, the flow lines, and the water body classifications. There had been an attempt to include the dams within this framework, but due to complexities and sensitivities with other partner agencies, we've decided to eliminate that from this process. In order to account for very large-scale anthropogenic or regulation human-driven actions, the National Weather Service forecast information, basins and points, and primarily those for reservoir locations, will be integrated into the NHD Plus, and forecast downstreams of major points of diversion or operation will be used to replace information coming out of the NIFI hydrologic modeling framework. And then a major component of this is integrating not only with the USGS Water Watch and NWIS National Water Information System points, but also with the FEMA National Flood Hazard Layer, allowing us to guess at the magnitude and extent of flooding when hydrologic conditions are higher than normal. Next component of NIFI is the hydrologic forecasting system. And this is very exciting because it couples some of the emerging capabilities from the National Weather Service in the form of this image here you see on the upper left, the high-resolution rapid refresh atmospheric model. This is a 1-kilometer atmospheric model producing rainfall, temperature, fluxes, wind information over the CONUS. This is then coupled within the WRF Hydro framework developed by Dr. David Gotchis and his colleagues at the National Center for Atmospheric Research to operate the NOAA MP land surface model. Output from the NOAA MP land surface model in forms of unrouted runoff is then mapped back to the NHD Plus catchment, and the node-to-node relationships within the NHD Plus version 2 that Al spoke to are used by a sub-algorithm called the RAPID model, developed by Cedric David while he was studying with Dr. Maidman at the University of Texas, Austin, to route the water using the Muskingum equations. And finally, the last component of the hydrologic model is the intersections of the impacts, mapping it back to both the catchment scale as well as the FEMA flood hazard layer data. I will say that cobbling this system together has been facilitated in no small part to 2 of Dr. Maidman's graduate students, Fernando Salas and Marcelo Somas, both at University of Texas. Marcelo is actually a postdoc. And we really would not have been able to get to the place and time we are with NIFI today if it hadn't been for their dedicated efforts. like I said, that last step is coupling this with a flood risk zone. So this is using the FEMA flood hazard layers within the NHD catchments to map the locations of expected flood impacts. And as we move forward in time, not only generating runoff information is a goal for the National Weather Service, but getting to the end point where, as data becomes more and more available through efforts led by the USGS, such as the 3D elevation program, actually acquiring LIDAR scale data, LIDAR to drive data at the scales necessary for dynamically generated inundation mapping. This will be explored through some elements of the National Flood Interoperability Experiment. Programmatically, the NFI, or Interoperability Experiment, has been going on for approximately 10 months. Beginning on June 1st, we operate the Summer Institute, and this is an exciting time when we bring students into the University of Alabama, as well as into the National Water Center, to really refine, develop, and push on this system, explore these new capabilities. Moving forward, out of the modeling component, the National Flood Interoperability Experiment will explore emerging web services, enabling us to better establish a system combining multiple components. In this case, we'll leverage the capabilities of ArcGIS Online to explore conflation of model output with other geospatial data sets. We'll leverage Quasi and the HydroShare project to explore the issues of publishing and making available very large data sets. As we prepare for onboarding the WRF Hydro system within the Weather Service Operational Supercomputing System, or WCOS, we are blowing the doors off of hydrologic data. In fact, if we export all of the data from WRF Hydro, all of the runs, it's on the order of magnitude of about 3 terabytes per day. To put that in reference, the outputs from the atmospheric models are on the order of 3 to 5 gigabytes per operational run. So we're really, by going to these very high spatial scales, 250-meter grids, and high temporal scales, 1 hour, we are really creating out of whole cloth a new large data issue. Then finally, we're exploring additional components of dissemination. This is within the NFI, we will leverage the work done by the CI Waters project, principal investigators Dr. Norm Jones and Jim Nelson at Brigham Young University, and their TETHIS platform, which allows a visualization of and plotting of streamflow hydrographs at any of the 2.67 million NHD plus streamlines across the country. Within the Weather Service, there are 12 weather forecast offices that will this year begin adding to their Twitter feeds static images of the NHD plus flow lines in tiny URLs that will be disseminated via Twitter. So we're moving in the right direction. We're moving towards using the language of the National Hydrography Dataset to really begin to define where impacts are, where the flooding is, and communicate that in a more geospatial nature to our users. I mentioned the Summer Institute a little bit prematurely. This is a effort that is really exciting to me. Not only are we looking at the NFI to explore a new methodology for developing modeling, but to establish a new paradigm for working with academia to help foster the development and growth of the water resources engineers, hydrologists, and forecasters that we'll need to drive the systems tomorrow. The NFI will start off with a 2-week boot camp on June 1st. It will run for approximately 7 weeks, and it will culminate with a capstone event July 15th through 17th. This capstone event will also coincide with the Quasi Hydroinformatics, a model on data interoperability from theory to practice conference. This is open to the public. Registration is required, but if you'd like to know more, if you'd like to get a hands-on view of the next generation or glimpsing the forecast of the next generation flood modeling, I'd encourage you to attend. And who wouldn't want to go to Tuscaloosa in the middle of July? I hear it's a wet heat. People often ask us, what is NFI for the Weather Service? And I use this slide as a summary. It is a community initiative. It is the brainchild of Dr. Maidman, but has been supported by a groundswelling of other federal agencies, private partners, and academic sectors. It demonstrates an initial set of water-related data services using community standards. It will demonstrate the future of real-time flood simulation and mapping using cutting-edge tools and technologies. It is also a prototype for a project-based interdisciplinary educational model for emerging scientists and technologists. The semester curricula and the NWC Summer Institute are two really exciting opportunities for us to engage with the next generation of forecasters and hydrologists. And these are just some of the organizations that have been involved: University of Alabama, University of Texas, NCAR, and our colleagues at the USGS, not only in the core science group with Al Ray, but across the water and water information groups. All of NFI, though, I will say in summary, is predicated on this ability to have a national hydrofabric, or in this case, National Hydrography Dataset. Finally, this is the first example of leveraging the National Water Center as a interagency, multi-agency, and national asset. The mission of the National Water Center is scientific excellence and innovation, driving water prediction and decision-making for a water-resilient nation. What we hope is that this is a center for collaborative research and development, a center for nationally consistent operations that complement the current capabilities of the weather forecast and river forecast centers across the country. It will support the river forecast centers through robust data services, and it will support mission-oriented research and development. As I said earlier, it's a catalyst for engaging academia. It's a proving ground for exploring emerging science and technologies, and it is an effort to not only engage in research to development, research to operational information exchanges, but also that operations back to the research community exchange, helping us inform the development community, the academic community, what our missions are, what our gaps are, what our science and services needs are. And so by doing so, it's a very symbiotic relationship. I believe that's all I have in terms of the review of the NIFI. And Al, I believe now we have time for some questions.
Yes, Ed, we've got time for questions. We have actually plenty of time here for questions. So go ahead and type your questions into the Q&A box.
Al, our first question is from Danielle Favreau from Idaho. She asked whether or not land disturbances are going to be incorporated into this, such as wildfires, and how wildfires might disturb the land and change the dynamics of the flooding.
Well, I'll take that answer. I'll take that question. The short answer is that within the NIFI itself, the parameterization of the land surface is relatively limited to what we have available to us today in the National Land Cover Dataset. The longer-term answer is that as we transition from NIFI to the operational systems within the National Water Center, that substantial amount of research and dedicated development activities will be geared at answering that question. So real-time ingest and reparameterization of burn areas is probably at the tip of that. That's one of the first things that we can do just in terms of the availability of burn scars from the BEAR teams, wildland fire delineations from Interagency Fire Center, but longer term, this can grow to include longer-term changes in land use, land cover, as gathered and sensed by the USGS AROS Data Center. So data assimilation for both the short-term phenomena and longer-term phenomena will certainly be included within the modeling system that's kind of being glimpsed at here with the NIFI.
So do we have any more questions from people? Now's the time to ask.
You're not seeing any others right now, Al, so if you'd like to ask a question, just type it into the Q&A part of the screen.
All right.
There are a couple questions coming into the chat section that you might want to take a look there as well, since they're coming in there.
Okay, so here's a question from Charlie Palmer. I think this is actually for you, Al. For states lacking NHD Plus as well as comprehensive stream gauge network, will a white paper be assembled to help encourage the needs of financing these data networks?
So I think the question is, I guess, is have we written a white paper on trying to finance this? I guess we haven't really written a white paper, but within USGS we are planning on, I mentioned this earlier, building NHD Plus for the high resolution NHD. Now you say for states that don't have NHD Plus right now, the only state that doesn't have it is Alaska. And Alaska is quite challenging just because of the real lack of data up in Alaska. We do have a lot of activity going on in Alaska with building data for NHD and also the elevation data. There's a very active program of acquiring IFSAR data, which is 5-meter resolution data that's being acquired for the state of Alaska. I think we're about a third of the way through Alaska right now. Maybe one of the other people online knows a little bit better of the status of the IFSAR acquisition. Once the IFSAR is collected, NHD data is being extracted from that, and that's quite a complex process. But it is happening, and so eventually we'll have NHD data, really good quality NHD data up in Alaska, and we'll be looking at building NHD Plus data from that. I hope that answers the question.
Yeah, and then we have a question from David Gilbert who asks, if we have an area that is interested in being a pilot for this initiative, how can we get involved?
I'll jump on that.
Yeah, go ahead.
I'm not sure if this is referring to the National Flood Interoperability Experiment or the broader term, the broader set of emerging capabilities coming out of the National Water Center. If that's the case, for the NIFI, this experiment is pretty well set in stone for this year. I will say that we endeavor to do interoperability experiments in the future, and we'll broadly advertise that as we did this year through the American Water Resource Association. So look forward to the meeting in November to learn more about the results from this year's work and then how to get involved next year. If it is about the more broader capabilities stemming from the National Water Center, well, that will be, we aim to provide those services everywhere. And through the evaluation phase, we will certainly work to develop prototype data sets that facilitate evaluation by not just internal weather service partners, but the broader federal community.
All right. So we have a question here from Kevin Roth that actually might be appropriate to your co-chair roles on the subcommittee for spatial water data relative to OMB, FGDC, and the Advisory Committee for Water Information. How can we make this information more available to OMB, for example, to help with funding and support? So maybe just expressing where the NFIE and the OWDI in general fit in relation to some of those other acronyms.
So, yeah, do you want to take that, or do you want me to?
You want to jump on it? I don't have a great answer for how we interact with OMB.
Right.
The short answer is, or perhaps the safe answer is, we will work through our respective agencies to communicate either necessities requirements through our budget process that tie back to the NHD, so that they can be considered for appropriation. I don't know. I know, Al, that from the NOAA perspective, we have been successful in garnering support for a FY15. We're appropriated for an FY15 activity that directly requires NOAA to do this work. It's called the Centralized Demonstration Modeling Project, and you can find that in the President's budget. I think the strength here is that NOAA and USGS told a story of efficiencies gained through interagency collaboration. So maybe that's part of how that can be successful.
Yeah, I think that's good. And I'll just add that there's an effort going on called the Open Water Data Initiative that's being led through the Subcommittee on Spatial Water Data that Ed and I co-chair. And that's getting a fair amount of notice up at fairly high levels. We've done some briefings. We've done a number of briefings about the Open Water Data Initiative. And this NFIE is one of our our use cases that we're looking at in Open Water Data Initiative, along with a couple of others. And I think it's getting a lot of attention. There have been budget initiatives, but you know, we all know there's money in the President's budget, but we all know that doesn't always translate to money in the final budget after Congress gets through with it. So you know, I think it's getting quite a bit of attention, and I'm expecting that things are going to start shaping up pretty well, hopefully, into the future. About as much as we probably should say.
Okay, then we have a question from Kate Streva. She says, do you foresee the possibility of end users being able to model for a specific type of storm or rainfall event, and then exporting these as polygons that could be used in a GIS?
I'm not sure if that's directed towards the modeling efforts demonstrated through the NIFI or through the flow calculations that Al spoke to. I'll answer the former. The nature of the forecast system will be such that it will attempt to do this nationally. It can't be operated by an end user. It's not that type of a model. It's more analogous to how the atmospheric models are developed. So grids are generated on the operational supercomputer and then provided to forecasters. But to answer the latter part of that question, we hope that as the skill in this type of operational modeling system is demonstrated and characterized, that it will greatly influence the ability for the end forecaster at a weather forecast office to better delineate a flash flood polygon with much more granularity, not only in spatial scale but in temporal scales. And Al, I don't know if you want to speak to operating the NHD plus flow calculations for specific events.
Well, it's interesting. We've had some discussions about that just in the last couple of days about kind of a code repository, or there's this concept within the Open Water Data Initiative for something called a marketplace of tools and code. So it's definitely something that's on the radar. To be able to make tools and databases available. The Open Water Data Initiative is really focused on trying to do that with both the tools and the data. So I think there's definitely an effort going on in that direction.
We have two more questions up. First question is from Steve Nachero. If an agency wanted to build tools that use the databases and tools, what is the process to help facilitate the architecture, development, and deployment of the applications? I'm going to speculate that relates to the NFIE.
Oh, I was going to speculate that it was geared at the NHD. That's a good question. I don't have an answer off the top of my head, mostly because we don't know what the NIFI is going to look like. I will say that one of the broader goals of the National Water Center is to cultivate something equivalent to the weather enterprise for water resources. And so I would say that the sooner that we can begin that dialogue with other agencies and with the private sector about how they can add value on top of the underlying data sets developed by next generation forecasting tools, the better we'll all be.
All right. There's actually a question came to my mind as well. This one's from Cindy Rachel. Will there be comparisons made between the NFIE and static maps created by the USGS Flood Inundation Mapping Group? Most, if not all, of those maps are produced from running HEC-RAS, not NHD-based, so it'd be interesting to see how these compare.
Yeah, I think that's an interesting question. We certainly will put the output from WRF-Hydro through a very robust evaluation framework as we move forward with that initiative. In terms of the NFI, I think that can certainly be done. I don't know that it's specifically in the student project planning, but if that's something that I can talk with my co-leads, Fernando Salas and Marcelo Somas, that will actually be responsible for the experimentation itself. The other aspect of the NFI that I think is exciting is exploring how a hydrologic model at the national scale on the NHD can be intersected with local and regional hydraulic models. So perhaps making interoperable the NHD hydrology or the NFI hydrology and the hydraulic analyses from underlying RAS models.
Okay, I think we probably need to wrap it up at this point. If you have more questions, we'll leave the question and answer open here for just a little longer. I think it'll be open as long as we keep the meeting open. So if you want to ask some more questions, go ahead, and we'll also we'll get written answers to any of the questions that you ask, and we'll post those on the website in the next few days, hopefully, after we get this all wrapped up. We'll also post the presentations out on the website as well. We'll be posting the recording, but it takes a while for us to do that because we have to do closed captioning for Section 508 compliance. So that'll take longer before we can get the recording posted. So I just want to wrap up, and I'd like to announce that the next session in our hydrography webinar series will take place on July 30th. And if you could, before you leave us, take a moment to answer these short polling questions. There's 4 short questions there. On the poll that you should be able to see there. It should have popped up for you. It'll help us help guide us as we design future webinars. And if you could answer those before you leave today, we really would appreciate it. Finally, I'll just point out again that the recordings and presentations will be posted to this website that you see there on the screen. Again, there'll be some delay for the recording, but we'll get that up there as soon as we can. And thank you all for joining us today. Appreciate you taking the time. Apologize for some of the problems we had with audio, but hopefully we'll have the recording up soon enough if you weren't able to catch the audio. Thank you very much, and we'll consider it adjourned. Okay, so we can probably stop the recording, Allison.